students in the lab right now, what they're doing, they are going to measure the flow of sand, and we have a setup. Probably next week will be like the very first prototype done. We want to look at 1 million particles of sand. We have spheres. We have spheres of glass. Some of them have 100 micron diameters, and some of them they have 500 micron diameters. So we want to measure the flow rates in the experimental setup and then in the simulation to see if they match. And I guess this is pretty much, yeah, that's it. So do you have any questions? I ran 25 minutes late.
So in these simulations that you're showing here, this is some sort of an explicit integrator that takes you forward in time.
Right.
That's the reason why it just sets up so well on those processors.
Because the reason why it sets up so nicely is that the collision detection we parallelized it and can be done in parallel. And then there is a so-called complementarity problem. It's solving an optimization problem where you compute the contact forces between every two particles that interact. And when you compute this contact force, it is an iterative process. You keep improving the value of the contact until every contact is happy. So this is done. You do the same thing for every single contact because there's no special contact. All of them are the same. So you have millions of them. So all of them they get executed in parallel. So that's why it's so good to do it on the GPU.
So when you transfer to this, then it knows, every particle knows what its nearest neighbors are, right? It isn't having to search for anything. There's no.
No, we do the collision detection. Collision detection tells it who's colliding with whom, the normal, the point of contact, and all that stuff. We compute that.
That's what's going on in the GPU.
Right.
But that doesn't require any kind of conditional or anything like that? You're just literally...
Oh, no, it has conditionals, but it has the same conditionals on everything. On everything.
Yeah, okay, got it. Okay. All right. Another question, which is, if you set your software up to run this way, then how do you write the software to run on any one of those architectures that you described there? Do you just have conditional compiles or something like that that says, I want to run this on Blue Gene?
No.
And I want to run it on this, or do you have to basically hard code it to work on?
Hard coded.
Okay.
Unfortunately, I don't have an IBM Blue Gene L. It'd be nice, but so I'm a poor guy. All I have is, as a matter of fact, we went to NVIDIA. I told you at the beginning of the month, and NVIDIA we applied and they donated for, like, we submitted the proposal afterwards, and we got the set of 24 C1060 GPU cards. So we are putting together a cluster, and that will be the architecture that we're going to run it on. And as a matter of fact, I have here, let me see if...
Well, there's this Blue Waters project at NCSA.
Yep.
That you're probably familiar with, probably more than I am.
No, not really.
Oh, well. But that's a very big computer.
That's a very big computer.
And you know the story behind this, right? I mean, the NSF has given them $200 million along with IBM to build this computer, and they really don't have applications that will run on this that will scale. And they're desperately looking for people that can actually know enough about this to make good use of what they're building.
What is it? Is it like a GPU supercomputer?
No, it's not a GPU. It's an IBM machine that is proprietary right now, but I have fairly good information about what it is. And
I was at UIUC in July.
Okay.
And I spoke with some folks there about it. But yeah, that's a very good thing, and I'm glad that they pay the money to do it. But I cannot afford something like that, and.
Well, it's not a matter of you buying it. I mean, they bought it.
Right, but the thing is that I need to develop them code that is suitable to that architecture.
That was the root of my...
and I don't want to do that.
Okay.
Because so this machine that we're putting together, it will be a 21 teraflop machine.
Okay.
And right now, it's single precision, okay? So it's not double precision. If you look at the list of 500 fastest supercomputers in the world, this would be a 380 or something like that. So, and it's going to cost something like $50,000.
Right.
So why would I, invest 200? The entry point, the IBM Blue Gene L entry point with 1,024 dual cores is $1.4 million. And now
I realize that. I'm not arguing. It's not a matter of price. The price, it's already been purchased, and so the question is whether it's a petaflop computer, right? So
right.
You've got a factor of 50 over what you're doing now.
I agree. But then the question is, if I go there, what will be the development tools that I have? What will be the debugger? What will be the profiler? So there's some overhead with moving from a platform to another one. But to answer your question, this is specific to GPU. Yeah. There's one thing that is not specific, though, to some extent. For instance, right now, this is one of the projects that I'm working on, and I might get back with you here because you like programming and such. One of the projects that I'm working on, so this class that we're putting together, it will have six machines. Each one will have 8 cores, but it will be 16 because it has this hyper-threading technology. So it will be 16 cores on 6 machines, so it will be 96 cores. And each machine will have 4 GPUs, which means another almost 1,000 cores. So I'm putting together now a software stack where first you have MPI work here at the top, and then you have OpenMP here in the middle, and you have CUDA here down at the bottom. So this is something that is not necessarily specific to NVIDIA, this software stack, because you have MPI, you have OpenMP. This is, when you start branching into clusters, it doesn't really matter if you have or you don't have a GPU. I just have to partition a problem in a manner that is amenable to cluster computing. So if any of you would be interested in looking at like giving feedback on what I'm working on, it would be greatly appreciated. And also I want to write a short paper in probably like 4 or 5 months about just reviewing p-threads, reviewing OpenMP, TBB, CUDA, MPitch, and what they are good for and what they are not good for. Also, I would really appreciate if any of you would like to read it and provide feedback. It'd be good. And also, I think in 1 year, probably in the spring of 2011, I'm going to teach again that high performance computing class. And if you're around, and if I am around because I'm not tenured, then it'd be good if we make that happen. So if you want to get the presentations are there. Or email me and I'll send you the links.
Email them to me and I'll put them on our website.
Yeah. Do you have any other questions?
I have one.
Yeah.
So if you're just trying to understand the programming model between like these blocks and threads and everything, so if you're going to do like something that I run into, like a Monte Carlo kind of calculation, is each like particle then like a thread, and then you like cluster particles?
It depends on how you can. If you have like a let's say that
just kind of a nominal kind of.
So I think if you have like an application that demands a lot of memory and it has a lot of it's not a simple and trivial application. Okay, in other words, it's not like a hotspot in an application that is clearly parallel and you can parallelize. Then if that's the case, you use the GPU. But if it's like, let's say it is Abacus. or Fluent or some humongous piece of code. There's no way you can have that ported
Right.
down there, okay? So then, if you have the letter, like the abacus type, then you can go to that cluster, and there, that cluster is super useful, because you can run the Monte Carlo and big, heavy application on each node, okay, in parallel. So that's, I don't know if I answered the question, but on the other hand, if you have one application where there's a part of the code that it is very compute intensive, and it fits the single instruction multiple data paradigm, there you can go to the GPU. And by the way,
Right, so like I do like multi-physics kind of computing. So you have like hydro on one level, and then you're going to do something else with the Monte Carlo method. So you just need to farm out like a bunch of particles to do radiation transfer.